doing some labs on gases. We're going to do another one tomorrow. And so the first lab we worked on was basically looking at all the different laws that people have worked out to describe the relationship between one way we measure gases to another way we measure gases. And then on tomorrow, we'll look at how we link all of them together into like sort of one massive, not terribly massive, fairly straightforward equation. But it's an equation we can use in a lot of different ways to work out a lot of different things. So, chapter 8. So first we'll just look at the different states of matter. We may think we know what's a gas, what's a solid, what's a liquid, but sometimes there's some things sort of in between. It would like, sort of make you scratch your head, like a gel, that sort of thing, like, well, what is it? We'll learn the differences between them. Learn how we measure the pressure of a gas. And then look at the gas laws and how they were originally discovered. You sort of work that out on your own. And then basically what we're going to do is take all those separate gas laws and, like I said, rearrange them into sort of one big ideal gas law, we're going to that it's called. And then go over why gases have that particular chemical properties. Why do they change? Why does the pressure increase with temperature? Why does the volume increase with temperature? Why is it that every mole of a gas has the same volume? It doesn't matter what the mass is. We'll go into like why that is on a molecular level, and then finally we'll learn the sad truth that there's no such thing as an ideal gas. Every gas has some deviation from what we call ideal behavior, because ideal behavior is based on gases having no interaction, gas molecules having no interaction with each other at all. And that's not the case. Even gases are going to interact with each other occasionally. And at very high pressure, we basically force them to interact with each other. And so we'll see that like at very high pressure or with some very unusual type gases, we'll see some deviations away from what normal, sort of so-called normal gases would behave. So very, very simply, how do we distinguish gases? Well, I mean, it seems pretty obvious, right? But these are some of the things that you can actually point to specifically to say that this is a gas and this isn't. Now we know the gas volume changes significantly with pressure, like a lot. If you change the pressure on a solid or a liquid, they basically don't change at all. In fact, who's heard of hydraulics? Must have heard of hydraulics, right? Hydraulic brakes, hydraulic whatever. Hydraulics are basically based on the principle that if you fill a tube with water, you can put tremendous amounts of pressure on it and it won't change its shape. It won't change its volume. And that's because liquids do not change their volume when you put large amounts of pressure on them. Another thing that changes significantly for gases is the volume changes significantly with temperature as well. And that isn't unique to gases. We know that when you drive across the Golden Gate Bridge, the Bay Bridge, or whatever it is, as you're driving across, it goes click, and then click, and click, and click. There's gaps in the bridge. Anyone know why there's built-in gaps in the bridge?
To account for the heat during the summer.
Right. What happens in the summer?
It's really, really hot.
No, but what happens when it gets hot? What physically happens to the bridge?
Does it expand?
It expands. Yeah, the metal and the pavement and everything else expands. Yeah, well, summer in San Francisco, that's kind of a joke right there. But anyway, yeah, when it gets hot, and it does occasionally, um, solids will expand. And if so those gaps weren't there, basically the bridge was sort of, push its in on itself and you get cracks all over it. And so you leave these spaces to allow for the bridge to expand when it gets hot and then to contract when it gets cold. But gases will expand and contract much, much more than solids and liquids do. 50 to 100, even more times greater. And you can see that. I've mentioned the example of putting a balloon in liquid nitrogen. And if you haven't done it, you really should. It's a lot of fun. So you fill up a balloon that's this big, and then when you put it in liquid nitrogen, basically it looks like it's empty. Looks like there's no gas in it at all when you take it out, because the volume has shrunk to such an extent that you almost looks like there's nothing there. But then when it gets back to room temperature, it re-expands to its original size. And if you heat it up even more, the balloon will get even bigger and until it breaks. Another big difference with gases, they flow very freely, which like flow, a gas. Well, yeah, if you can say they can just move from one place to another simply, they do. Liquids flow freely. Solids don't flow very freely at all. Gases have very low densities. So remember, the density of water is 1 gram per milliliter. Now the density of a gas would be about anywhere from 50 to 100 times less than that. So we're dealing with very, very low densities. And another unique property of gases is that they could form a solution in any proportion. And then you may think to yourself, a solution of gases? Well, yeah, gases form solutions just like liquids do. I mean, what is a solution? Anyone tell me what a solution is? I mean, we know what they are, but can we actually give it a definition that makes sense? Oh, someone's looking it up. What is a solution?
Liquid?
No, just any solution. Solids make solutions too.
A mixture?
Yeah, basically. Yeah, I mean, it's really just a mixture where anywhere in that solution you can take out a piece and there'll be a little bit of everything in it. Basically, that's like a homogeneous solution. So like salt water, as long as there's nothing at the bottom, and everything's soluble, everything's in solution, we say that's a homogeneous solution, because I can take some from the top, I can take some from the bottom. Anywhere in that glass, I'm going to get water and salt in the same concentration. That's also true with air. Air is a solution. What do you think the solvent is? Because like every solution has to have a solvent and a solute, right? The thing that gets dissolved. What do you think the solvent is in air? I mean, think about what makes up air.
Is it nitrogen?
It is nitrogen. Very good. Yeah. Nitrogen is around 78% or so, or I think it's a little less than that, of the total. And so basically what we're dealing with is a solution where nitrogen is the solvent and everything else is basically dissolved into nitrogen. And we just say nitrogen's the solvent because it's the most abundant. And so unlike liquids, we can take any gases and put them together and they'll mix. I mean, as long as you don't have a chemical reaction, like if you have hydrogen and oxygen mixed together and you set off a match, they're no longer mixing, they're combining, they're making something else, they're making water vapor or even water liquid. But if you just leave them to themselves, they'll just freely mix with each other. And we know that's not the case for liquids. If you mix gasoline and water, they'll separate. If you mix oil and water, they'll separate. They won't mix. But that's not the case with gases, where they'll mix in any proportion. So how do we measure some of the things about gases? One of the first things we sort of deal with when we're talking about gases is pressure, because we don't really talk about water pressure much unless we're diving or something like that. But gas pressure is very important. Gas pressure basically tells you how much gas you have in an enclosed volume. And what does pressure mean? It basically just means it's the force on a particular area. And so in this case, the area would be the sides of the container. So this is the sides of the container where I have my gas, and the force would be the gas molecules hitting the sides of it. That's what leads to gas pressure. So atmospheric pressure arises by the gases floating above the earth being brought down by gravity, and they exert a certain pressure on us. But as we move up into altitude, we know that the atmospheric pressure goes down. So like the top of Mount Everest is only about, I think it's around 55 to 60% of the atmospheric pressure that we have at sea level, which is why it's so difficult to breathe up there. You need to bring oxygen, because one, you're working really, really hard. Your muscles are working incredibly hard to just climb, or even just to walk around. And so you need more oxygen than you would at sea level anyway. And there's like only 60% of the oxygen you normally get. So that's why it's so dangerous to go mountain climbing without oxygen when the atmospheric pressure is so low. So this is one of the ways we use to measure pressure. This is like an old school way to measure pressure. And there's actually one of these in the lab. So I kind of like to dig this out because it's really cool. You don't get to see these much anymore. This is a mercury barometer. And a barometer is just something that measures temperature. Something that measures pressure. In fact, the height of this mercury column is a measurement of pressure by itself. And so what we do is we have a dish filled with mercury. We put it in a column, and basically we pump out any air up here. So there's a complete vacuum above the column. So the mercury is going to be pulled somewhat up the column, and it's going to be pushed even more by the atmospheric pressure. So basically what we're looking at is how high will this column of mercury be pushed? And if the atmospheric pressure goes up, it pushes the mercury even higher up the column. And if the atmospheric pressure drops a little bit, the level of mercury drops. And so in the old days, there's still some places, mercury is just measured in, or gas pressure is measured in millimeters of mercury. And this is also called torr. Torr is a very common measurement of pressure. And so like if you're listening to a weather forecast, they will give you the pressure, the atmospheric pressure to tell you, because if the atmospheric pressure goes up, generally that means good weather is coming. If the atmospheric pressure goes down, generally means bad weather's coming. And so it used to be in millimeters of mercury. Anyone know what it is now? Does anyone even listen to a weather forecast like ever? Or well, probably looked at it on your phone, right? If you look at the weather forecast on your phone, do you see what the pressure is in? Quiet.
Millibars of mercury.
Millibars. Millibars, yeah. That would be this. So it basically it's the number of millimeters of mercury. But I think the common way now, I think, is kilopascals. So yeah, we'll go through all the different derivations of pressure, but like, yeah, believe me, there's a lot of different ways to measure pressure. Basically, because a lot of different people developed ways of measuring it and then named it after themselves. So we have all these different measures. But what we're going to basically deal with is atmospheres, because that kind of is the easiest way to sort of get your head around. So 1 atmosphere is equal to 760 millimeters of mercury. So when the atmospheric pressure pushes a column of mercury up 760 millimeters against a vacuum, we consider that 1 atmosphere. And so basically we're going to be using that. If we get measurements and anything else, we'll just be converting it to atmospheres, because it's just an easier, like 1 is a much easier number to use than 760 or all these other numbers that you'll see in a little while. So 2 basically different ways that we used mercury to measure the pressure is 1, either we had closed end with vacuums on it. So on this side we have a flask with nothing in it, and we have a vacuum here. And then we let gas in and see how much it pushes this column of mercury. And we just looked at the difference in the height. So if it pushed it up, so if this measurement was 250 millimeters and this measurement was 50 millimeters, we'd say that the pressure of the gas inside was 200 millimeters of mercury. And then we just convert that to atmospheres, and that's how much pressure we would have. Or we have this other method over here where we look at how different is it from the atmospheric pressure. And so we just look at, basically both of these, we're looking at a difference. One is a difference against a vacuum, and the other is a difference against the atmosphere. So if we give the atmosphere at 760 or whatever it would be, we'd measure it. You could actually measure it down to like a couple of tenths of a millimeter. And then just measure the difference. If it's less than an atmosphere, you're going to have this difference over here. And if it's more than an atmosphere, you're going to have this difference over here. Basically, all these different ways of measuring pressure are just against either a vacuum, where it's 0 pressure, or against the atmosphere, which would be 1 atmosphere of pressure. And these are the different units. I mentioned there's a lot of different units of pressure. And some of these you may be familiar with, like if you've ever, it used to be, if you check the pressure of the tires in your car, what unit of pressure is that? No one's ever checked their tire pressure.
PSI.
PSI, what does PSI stand for?
Pounds per square inch.
There you go, yes, this one. And so you normally inflate your car tires to somewhere between like 35 and 50 PSI, generally, depending on, if you have like racing tires, you want to, or if you want to have really good traction, you lower the tire pressure. And 1 atmosphere is around 15. So basically you have between like 2 or 3 atmospheres of pressure inside the tires of your car. So atmosphere is the one most easy to understand. 1 atmosphere is also this much pressure in pascals. And pascals is something that physicists generally use, because there's lots of different ways to measure pressure. There's gas pressure, there's pressure that 2 pieces of iron or whatever welded together have pressure on each other, and so you look at the amount of force over a unit and all that kind of stuff. So generally that's used in physics more than chemistry. We normally use torr or millimeters of mercury. And then here's bar right here. And bar is basically kilopascals times 10 to the 5th, or divide it by 10 to the 5th. So it's pretty close 1 bar is pretty close to 1 atmosphere. You can see there's not much difference. And so a millibar would be this divided by 1,000. But basically, so what we're going to do, you don't have to memorize all these different ways to convert. You'll get the conversion, but you may not always get, if you get a question on a test or something, it may not always be in atmospheres. It could be in torr, it could be in millimeters of mercury. And you'll have to remember that if you want to figure out your question in a particular way, you've got to do a conversion. I mean, that's basically, chemistry is all about conversions, right? If you've been paying attention so far. So here's a problem. Here's just a simple way of doing these sorts of things. So if you heat up limestone is just calcium carbonate. If you heat that up, you release CO2 and you're left with calcium oxide. So if you heat it up, and you can measure the pressure of the CO2 that is let off from heating the limestone. So when the system comes to room temperature, the difference in pressure is 291.4 millimeters of mercury. So basically, we need to figure out what is that pressure in torr, in atmospheres, in kilopascals, okay? And it's basically just substituting one particular unit for another. So 1 torr is equal to 1 millimeter of mercury. So that one's pretty easy. 1 atmosphere is equal to 760 torr. That's probably something that's like should stick in your head. So that one's fairly easy to do. Just remember, always put the unit you want to get rid of in the denominator and put the unit you want to keep in the numerator. I noticed a lot of people in their recitations and on their tests aren't putting the units in the conversions. And that leads to mistakes because it's very easy for someone to go 291.4 and you remember the 760 number, but instead you multiply by 760 and you get some huge number of atmospheres and your answers can be way off. That won't happen if you remember to include the units, okay? So always remember to do that. And then finally, atmospheres, 101.325 kilopascals in an atmosphere, subtract the atmospheres and you're left with that. Generally, we're going to be taking everything and converting it to atmospheres because I just find it's the easiest number. It's going to be a number that approaches 1, you know, and it's a number we can sort of wrap our heads around. We sort of get if someone tells you that a pressure is like certain number of kilopascals, you have no idea what that means. But if they said half an atmosphere, yeah, that kind of like, you know, you can actually wrap your brain around that. That makes some amount of sense. You know, kind of what that pressure is going to be. So these are the different gas laws that you all sort of basically solve for yourself and saw the relationship between the different units we use when we're dealing with gases. And as I mentioned when we're doing the lab, there's really only 4 things we have to think about when we're dealing with gases. And that's like the number of moles. Well, we need to figure out a way to figure out like how much gas is in there, how many moles of gas are in there. If we're going to do some reaction with gases, we need to know how many moles there are. Generally, we need to know how many moles there are more than we need to know the masses. Because as we mentioned before, it doesn't matter what the mass of a gas is, its pressure and temperature and volume are all going to be basically the same. And so really all we care about is the moles. And when we get gas, when we get a canister of gas, there's basically only 2 things we're interested in. What's the pressure inside here and how big is it? That's going to tell me how much gas is present. But then if I'm doing a reaction where I'm letting off gas, the temperature is very important because the temperature is going to change both the pressure and the volume, as you guys noticed when you were doing your experiments. So if I'm doing an experiment releasing gas and I want to measure how much is being made, I have to take into consideration whether I'm doing it at 0 degrees Celsius, am I doing it at room temperature, am I boiling something? All of those things will cause the pressure and the volume to be different, because what I need to figure out is how many moles of gas I'm creating. That's what I really want to measure when I'm doing an experiment. I need to know the amounts that I'm creating. So an ideal gas is one that exhibits exactly linear relationships. And if you did your experiments, you noticed that when you plotted things, it was a perfectly straight line, right? And all the points were like exactly on that line with no deviation. So your R squareds were 1 every time. Now that's what an ideal gas will do. It will give you exactly linear relationship with every single point on the line. But this is the real world, and gases don't actually behave like that. They behave really close. The characteristics of most gases are almost ideal. They're really, really close to a straight line. But so they're most nearly ideal at the ordinary temperatures and pressures that we're dealing with. But at very low temperatures and very high pressures, they start to behave and have different characteristics, and they deviate quite a lot from a linear relationship. Any questions so far with the difference between like an ideal gas and a non-ideal gas? So all the gases you guys were dealing with were ideal because you didn't see any difference. All the points were right on a line, or hopefully they were. But if we were doing them under very, very high pressures, I think the highest pressure we dealt with was like around 10 atmospheres. I'm talking about thousands of atmospheres of pressure. The kind of pressures you can only get when like you're taking 2 diamonds and pushing them together. When you have that really high a pressure, gases start to react strangely, shall we say. They deviate from ideal. So here's the laws you guys all figured out on your own. So Boyle figured out that the higher the volume was of a gas, the lower the pressure. If he had a constant amount, if he had a fixed amount of gas, so N, remember every time you did your experiments, you remember you had to fix 2 things? So in this particular instance, since we're dealing with pressure and volume, and the number of moles, and the temperature, if we want to figure out the relationship between any 2 of them, the other 2 have to be locked in. And so look at the difference, look at the relationship between pressure and volume. We need to keep this locked down and that locked down. So a constant amount of gas at a fixed temperature. So we can see that when we increased the volume, the pressure went down. And when we squished the volume down, the pressure went up. And that made sense because as we pushed the volume down in that piston, the gas in there would be making contact with the sides of the container more than if it was a larger container. And we know that the gas hitting the sides of the container is what causes pressure. So anything that causes the gas molecules to hit the container more frequently is going to increase the pressure. So we saw that there was an inverse relationship. And what inverse means is that basically the volume, numerator volume, is related to denominator pressure. You can think of it that way. So remember when we plotted volume versus pressure, it wasn't a straight line because they're not directly related. They're inversely related. So what do we have to plot in order to see a straight line with Boyle's law?
Volume versus 1 over pressure.
That's right. We had to plot this versus this. That is directly related. And that's what this symbol here means. That's what this symbol is. It means directly related. So volume is directly related to the inverse of the pressure. The other thing that does for us, and that'll come in real handy, is if we multiply volume by pressure, we get a number. We get a constant. And we're going to call that constant, as you'll find out later, R. We get a number that's always the same. So my V1, P1, so my initial pressure times my initial volume will equal my new volume times my new pressure. Basically, they're going to be equal to each other. And we can use that when we're deriving the overall law. But this is important. When we multiply the pressure times the volume, we get a constant number. So that was Boyle. Then Charles came along and saw that if you kept the pressure constant, like again, we saw like in the piston, if we pushed it down, so if we pushed down our piston till we got the pressure of like, 1 atmosphere or something like that. If we heated up the piston with the gas in it, the volume would increase, right? The volume, this piston would move backwards to accommodate the gases moving more quickly as the temperature went up. And so the higher the temperature went up, the higher the pressure went up. And so in this instance, the volume is directly related to the temperature. The two of them increase at the same. If one increases, the other one increases. If one decreases, the other one decreases. So what that means is if I divide volume by temperature, I get a constant. Because the initial volume divided by the initial temperature will equal the second volume divided by the second temperature. These two things are equal. And so they're always going to equal the same thing. My whatever volume I have divided by whatever temperature I have will always equal my second volume, whatever it is, divided by my second temperature, whatever it is. They're always going to be equal to each other. So we use this to also fit in to how we're going to put all the different gas laws together. So in this particular case, we could plot temperature versus volume, and that was a straight line. We could, because they're directly related. As one increases, so does the other. So in that instance, we did have a straight line between the two. And then with Avogadro, hopefully you guys figured out how to do the Avogadro's experiment. If you haven't figured it out yet, just send me an email. I'll let you in on the secret. Some of my students have done it already. They're so very smart. What this means is when Avogadro did his experiments, he noticed that when he had two reagents, he mixed them together, and they created X moles of gas. And then he measured the volume. And so then he would do another experiment where he had twice as much of each reagent that would make 2x amount of gas. And he noticed that the volume was exactly twice as much. And so he figured out that the number of moles of gas that were created was directly proportional to the volume. And so in this particular instance, volume is directly proportional to N, or the number of moles. And so when you do your plot for this one, you're going to plot N, or in your instance, like pumps of gas, however many pumps you do. Should be able to do at least 5 or 6, versus volume. And you'll see that with each pump, you get more volume, and they're directly related. And so if we divide V1 by N1, we're going to equal V2 divided by N2. Or, in other words, V divided by N is also a constant. So by putting together all the things that we multiply and be a constant, and all the things we divide to be a constant, we could put all the laws together in one super duper law called the ideal gas law. So you're going to hear this a lot, STP. And many of you are gearheads, you probably think STP stands for like some gas additive or something like that. No, in this particular, well, it does mean that, but in this particular example, it means standard temperature and pressure. Basically, a standard temperature and pressure means that is, if we convert everything to a particular pressure and a particular temperature, we can compare all sorts of different things. And so at 0 degrees C, that's the standard temperature. Now we usually think of standard temperature to be around 25 C, like standard room temperature. And for most things, that is the standard temperature. But for gases, for some reason, it's 0. So 0 degrees. Or, and remember, we don't use Celsius when we're doing gases. We always use Kelvin. So basically what you're going to be doing is adding 273.15 to everything. If you get a temperature, and it doesn't matter what the temperature is, negative or positive, add 273.15 K to it, and that'll be your temperature in Kelvin. So at precisely 273.15 Kelvin, 1 mole of gas at 1 atmosphere is about 22.4 liters. Any gas, doesn't matter what gas it is, 1 mole of it will take up that much space, okay? And we know this because we can measure it. Here's 3 different gases. First, I've got helium. Now, helium is basically the simplest gas, and it's pretty much one of the few gases that's monatomic. So, because helium doesn't react with anybody. So helium gas is basically an atom of helium. It's one of the few gases, other than the other noble gases, which are just atoms. And so if we have a mole of it, 1 mole would be 4 grams. So in this tank, I've got 4 grams of helium. It's 1 atmosphere, and I would have 22.4 liters of helium. Now here I've got nitrogen. Nitrogen's going to be heavier because I've got 2 of them and they're bound together. So it'd be 14 times 2, so 28 grams per mil. So this would be 7.5 times heavier than helium, like more mass. But notice the volume is exactly the same, 22.4 liters. And then finally, I've got oxygen, 16 times 2, that's 32 grams per mole. So now I've got 32 grams of oxygen in there, so even more, but the volume is the same. So we don't really have to, we don't do too many gram to mole conversions for gas because we don't measure gas in mass very often. We don't bother because it doesn't matter. What we really want to measure are moles because moles are the important thing for doing reactions. The mass of it is, we don't generally bother because no one cares what the mass of the gas is. So here's when we get to the ideal gas law, where we put all the different relationships together. We put the Charles law and Boyle's law and Avogadro's law and the Gay-Lussac law. We put them all together into one really pretty easy format, and I just like to call it PIVNERT. If you remember nothing else from this class, you'll remember PIVNERT, capital P. So P times V equals nRT. That's it, PIVNERT. And so you know what the P is, you know what the V is, and you know what the N and the T are. The only thing we haven't talked about yet is R. R is the number that holds it all together. And R is what you're going to be determining tomorrow in the lab. Basically, it's the magic number that connects all these other numbers together. And so if we just do a little bit of rearranging, and believe me, when you do these gas laws, you're going to be rearranging them constantly. So that's why I just memorize this. And then I don't memorize all the other ones. I just memorize that. And then I rearrange it when I need to. So if we need to solve for R, all we do is just divide both sides by N over T, and we get this. So R would equal the pressure times the volume divided by the number of moles and the temperature. And you get this weird unit, right? It's going to be a very weird unit because basically what you're doing is you're relating 4 different units together. And we've been dealing with, units like grams per mole or maybe, something like that. Now we've got one with 4 units in it, which makes it difficult to deal with sometimes. But now you understand why it's going to be even more important to have the units in your conversions, because now that we got 4 of them, it's going to be really easy to make a mistake, right? So if we have 1 atmosphere and 1 mole, and that's the standard temperature, and that's the standard volume, if we take all of those together and do our conversion, this is the number we get. So 0.0821 atmosphere liters. Yes, atmospheres and liters are going to be in the denominator because you can see they're both in the denominator. Moles and K for temperature are going to be in the denominator. Moles and K. And so the other way we can look at this is if we just get rid of R, PV NT equals R. What does that mean? Well, this is a constant. So my first pressure times my first volume divided by the first amount of gas divided by the first temperature is going to equal whatever my second pressure is and my second volume and my second moles of gas and my second temperature. That's what that means. So you don't even need to have R if you basically have the old pressure, volume, moles, and temperature measurements, and you have, like, say, 3 of the other ones. You have a new pressure. Hello. Okay. So if you have 3 of the units, you can always solve for the 4th one. Any 3 you can solve for the last one. Okay, that's basically what this comes down to. So PivNerd, that's what we're going to be using over and over and over again. It's basically the whole chapter. It's just remembering that PV equals nRT. That's really it. We get right down to it. That's why I say it's not going to be a particularly difficult or long chapter to get into, because what we really want to know is, if I measure 3 things, can I get the 4th? And yes, if you remember what R is. Any questions on the ideal law? You've probably seen that before. Am I right? Probably remember this from high school or from, like, whatever the last chemistry class you took, if you got to the gas laws.
Yeah.
This is, because, yeah, it basically means we don't have to remember any of them in particular. We just need to remember this. Because all of the individual laws, when you slap them together, comes down to this. And so we can just use this basically from now on for everything we need to. But we could also use it to figure out the relationships. Like, because we're multiplying P and V together, that tells us that P must be related to 1 over V. Because we've got P and T on opposite sides of the equal sign, that P must be directly related to T, that N must be directly related to P, that N must be directly related to V, because they're on opposite sides of the equal sign. And so we can use that information to sort of go back and figure out, well, wait a minute, what was the original relationship between them? All you need to do is just remember that, and everything else you can derive from it. So basically, this is like the magic formula. So here's typical questions you're gonna get on a test, and you're gonna use this particular formula to solve it. So if you've got like you got a helium balloon, it's your birthday or something, someone gave you a balloon. It's a big ass balloon. You can see it's got 15.8 liters. That's a big balloon. So you take it up to the top of Mount Hood. It's just outside of Portland in Oregon, where I went to school. And so when you're at the bottom of the mountain, you're pretty close to like 1 atmosphere of pressure. It was probably raining that day, so the atmospheric pressure is a little bit lower than normal. And it was 22 degrees. So you climb up to the top with your balloon, because like, hey, who wouldn't? And at the top of the mountain, you see the atmospheric pressure is lower now. Notice they're in different units. And the temperature is colder. Anyone who's done any mountain climbing in Oregon will tell you, it gets cold up there. Like in the winter when you're driving up to go skiing at the base of the mountain, it could be pretty warm. But when you get up to the top, it's going to be freezing. So the question is, what's the volume of your balloon when you finally get up there? And here you have all the information you need to solve it. So how are we going to do that? So what we're going to do is figure out what our initial and final measurements are, and basically convert them all to the same units. So we want to figure out what V2 is. We don't know what that one is, but we know what T1 is, and we know what T2 is, we know what P1 is, and we know what P2 is, but we need to convert everything to the same units. And for temperature, it's got to be Kelvin. Always, 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 always has to be Kelvin, okay? So we convert both of those to Kelvin. We convert this to atmospheres, and then basically we can just plug and play. We just put it into the equation and figure it out. So 22, we just add our 273, and 0, well, that's pretty easy to add. We get 273, so 295 at the bottom of the mountain, 273 at the top. So here's how we solve it. So we change our second pressure to atmospheres, and we just do that very simply by using the relationship of 1 atmosphere is equal to 760. And I really want you to remember that. Every time you do a conversion, you're just multiplying by 1. That's all you're doing. That's why it's essential to have the units in there. Because basically what you are saying when you do a conversion is that this is equal to that, because I've multiplied this by 1. So I haven't done anything to it. It's the same thing. So that's why I always multiply and I never divide, because my units are always in the right place. So when I do my conversions, then you use the relationship that we get from the ideal gas law. You remember that, so my PV equals nRT. So if I don't know what R is, I can still figure it out, because I know that the initial pressure times the initial volume divided by the initial number of moles, and that's going to stay the same, divided by the initial temperature is going to equal to the same thing on the other side, but all the second set of circumstances. So here's what everything's going to equal at the bottom of the hill, and this is what everything's going to equal to at the top of the hill, and we know they're going to be the same. So basically all I need to do is I can eliminate N1 and N2 because they're the same. I haven't changed the amount of gas in the balloon. So all I need to do is just isolate V2. So you're going to be doing a lot of sort of isolations here. So if any of you have trouble with that kind of mathematics, this is probably not the best time to be doing that, because basically we're just going to be doing a whole lot of solving for X, right? So it's just basically moving numbers around so we can isolate what it is we want to solve for. So in this instance, if I want to solve for V2, let me just clear everything off here. If I want to solve for V2, how do I do that? So I want that. That's what I want to solve for. Well, how am I going to do that? Well, I'm going to multiply each side by T2, and I'm going to divide each side by P2, right? And then plug everything in. I find out that my balloon has actually gotten bigger. Now, the temperature has gone down. So why isn't the balloon smaller? Because we know that when the temperature goes down, the volume goes down. So why is the balloon bigger at the top of the mountain? What's primarily responsible for the change in the volume?
The pressure.
Yeah, the pressure. We can see that here, right? This is the difference in pressure, and next to it is the difference in temperature. And so when we convert things to Kelvin, we can really see the temperature differences. Because if I look at the difference between 0 and 20 degrees, wow, that's like, that's a huge difference. But when you actually look at the real difference, it's only the difference between 273 and 295. That really isn't that much of a difference. But there is a big difference between 0.98 and 0.7. That's a much more dramatic difference. And so that contributes more to the change in the volume than the temperature does. And we're going to see that more and more. Like generally, unless there's some huge change in temperature, we're not going to see that much of a difference dealing with temperature. But pressure is going to make a big, big difference. So here's another one we can do. It's a very, very typical kind of question. So actually, this looks like kind of like I used to have a steel tank in my lab with about that amount of gas in it. Mine was filled with nitrogen. So here we have a steel tank filled with oxygen. So that's going to be kind of dangerous to have sitting around. Oxygen known to explode. So I have a steel tank. It has that much capacity. It's that much volume. And this time we actually do have a mass of oxygen. Generally, you don't get questions with masses of oxygen in it, but we can use that to calculate what the pressure is going to be. So in this instance, we have V, we have T, we have a mass, and we need to find P. So basically what we're going to do is convert mass into moles. You don't have to do that a lot, but occasionally you do. So that's what we're going to do here. So you take your volume. Here's our volume. That's not going to change. We convert the temperature to Kelvin just by adding 273.15. And you can see a lot of these they don't add the 0.15. I'd prefer you would, but it's not exactly necessary. I probably would add the 0.15 because, like I always say, use as many significant digits as you can until you get to the end and then round down. So I would use, the more significant digits, the merrier until you get to the end. So in this instance, we convert mass to moles. And so we know that that is 885 grams. So 885 grams divided by 32 grams for 1 mole, and we get 27.7 moles. And now we have everything we need. Now we just plug and play into PivNert. So the other thing we can do is if we just want piv, or we just want p, and we don't want, the rest of ivnert, we just move the volume to the other side. We just divide both sides. So remember, this is our magic equation. We're gonna be doing a lot of algebra, people. I got bad news for you. So if I just want to solve for p, I divide both sides by v, right? This becomes p by itself, and the rest of it's nRT divided by v. And then we just make sure everything has the right units. And there's lots of different expressions for R. So when you look this up in online, or you're doing these problems and you need to know what R is, make sure you use the right number for R, because you can see this particular value of R is atmospheres, liters, moles, and Kelvin. There are other, so the liters, the moles, and the Kelvin are pretty much going to stay the same. The pressure is going to be in a lot of different things. So there's R for torr, there's R for kilopascals, there's torr for bar. There's all kinds of different numbers. Make sure you're using the one for atmospheres. So it should be 0.0821, but there's a lot of different, depending on what your pressure is in, it'll change. So we just plug all that in, and then this is also a place to check and make on your units, because I have moles on the top and I have moles on the bottom on the top. So I can subtract my mole, I can get rid of my moles. Here I have Kelvin on the top, and I'm multiplying by something with Kelvin in the denominator, so I can get rid of Kelvin. I also have liters in the denominator, and on the top, liters are in the numerator, so I can eliminate those. Be really careful about that one. A lot of people will look at that particular expression and think that that Kelvin should be down here or something. Well, that's not the case, because this whole expression is in the numerator. So remember that. So if something is in the denominator here, what you want to cancel has to be in the numerator on the top. So what you have left, the only thing you have left, is you canceled everything out, is atmospheres, and it's in the numerator. So that's how you know you've set everything up properly, because you're looking for pressure. Atmospheres is the only unit left. It's in the numerator, and so if you do your math right, that's going to be right. And so again, when you do these sorts of questions on tests or in a recitation or whatever, if you set up your whole equation properly with all the units in there, and you make some dumb mistake, like I typically do, I'm using my gorilla finger that smashes down 4 numbers at a time. I make a lot of mistakes when I use the calculator. If you make a mistake with the calculator, let's say you come up with 7.54 atmospheres or something. Well, obviously you set up the equation correctly. You just made a dumb mistake, which we all do. And so you'll get most of the points for that question. On the other hand, if you just give me 7.54 atmospheres, you will get nothing. And so that's why I sort of urge you to set everything up properly, because basically I don't really care that you do the math properly. What's really important is that you know how to solve the problem. And if you set the problem up with all the right units in the right places, I know that you've figured out how to solve the problem. You just made a dumb mistake. Can we really penalize you for making dumb mistakes? I make more of them than most. I would say no. So any questions about how you do this particular kind of problem? You can see most of the time we sort of just plug things into PivNert. Sometimes we have to sort of use the relationships between the different units, but most of the time we're just sort of just plugging things in. No questions. I'm just going to assume that you're all brain geniuses and are just picking this all up. Like, you have no problems whatsoever. All right, your loss. Well, we're going to keep going. So now we're going to look at density. Remember what I mentioned at the beginning, the density of gases is really low. Anyone tell me why the density of gas is so much lower than either solids or liquids? Why is that? The atoms are the same size. In fact, the atoms of a gas can be much bigger than the atoms of a liquid. How come the density is so much lower?
Because the mass is not big.
No,
The
no, the mass of a gas can be huge. In fact, when you want to enrich uranium, you react uranium with fluorine gas, and you make uranium hexafluoride. So that is big. Uranium's a big molecule, and that is a gas. So by separating the lighter gas from the heavier gas, you can make an atomic bomb. So this is a big, big molecule, but it's a gas. Water, it's much smaller, but it's a liquid. So how come the density of that would be so low? Like
the
100.
volume,
The what?
the volume when we have on the top big number and in the denominator big number, when you divide it's gonna be small.
Yeah, the volume, right. I mean, the volume of this is much, much smaller. And so basically, there's huge amount of empty space. I sort of mentioned this to my class during the lab the other day. It's weird to think about, but I mentioned two things that don't make any sense when you think of them together. One is that a gas container is always filled because there's going to be gas all over it. Second one is the vast amount of space inside a gas cylinder is empty. There's nothing. There's nothing there. Both of these things are true at the same time. The gas cylinder is both full and it's empty. It's because there's so much space between gas molecules that really the vast majority of space inside a cylinder is empty. There's nothing there. And so the density of the gas is really, really, really low because of the space between the molecules. Water molecules are right up together, you know, rubbing on each other, interacting with each other. And gas molecules do not do that. So we can figure out the density of a gas. The density is going to be directly proportional to its mass. So the higher the mass, like this would be like a very heavy mass. This would be a very light mass. So we would say that the density of this gas would be much higher than this gas. Now they're going to take up pretty much the same amount of space. So the density is going to be directly proportional to the two. But it's going to be inversely proportional to the temperature. Why? Because the higher the temperature, the higher the volume. And we're dividing, and the density is mass divided by volume. So if the volume gets bigger and bigger and bigger, the density is going to get smaller and smaller and smaller. So basically, all we're doing is taking good old Pivnert and making a substitution. So our substitution, instead of having N for moles, we're going to have M for mass divided by mass over moles. Because in this instance, when I have a 1 over, if I have 1 over 1 over moles, that equals moles. So I'm dividing by moles on the bottom, which means my masses cancel out and we're going to have moles left on the numerator. So I'm dividing by them in the denominator. I know, a little weird, but it's one of those things we use in math to move things around. So instead of using N, I'm just going to use the mass divided by the molar mass, because that's the same thing. And so we can see that the density, because it's the mass divided by the volume, is also equal to the molar mass times the pressure divided by R divided by T. And so we can figure this out pretty quickly. So I do not memorize this. I just memorize this and plug in whatever I need. So in this instance, I would just plug in M divided by the molar mass. And I get me the same result, okay? Here's an example. So in a particular manufacturing process, we used to use these horrible things called chlorofluorocarbons. Oops, let me go back. Back. Come on, here we go. So we used to use chlorofluorocarbons, so we figured out they were destroying the ozone layer. So basically we switched out, and within 5 years, 6 years, nobody was using chlorofluorocarbons anymore. And so in this particular approach, a blowing agent, it basically just sounds like it is, just something that you can like put as an aerosol and push whatever it is you're reacting from one place to another. And so just use a CO2 instead, like pressurized CO2. So what is the density of CO2 in grams over liters at standard temperature and pressure and at normal room conditions? So a difference of 20 K, all right? So where do we start? First, we need to figure out how many grams we have. So here we go. So there's a couple of things we know just based on the information we have. So we know what the temperature is. Standard temperature and pressure mean both those two things. So this we don't need to do anything with. This we change to 273. And we know what the molar mass of CO2 is. It's that we can just look that up. So what do we do with that information? So what else do we know about what happens, how much volume does a gas take up at 0 degrees C and 1 atmosphere? We learned it a little while ago. Because if we're going to be solving PivNert, we need to know N. We need to know moles. But I don't have moles. What am I going to do? I have a molar mass, but I do have standard temperature and pressure, and that tells me something. What does that tell me? I don't have a volume, so I don't have a volume, and I don't have number of moles. How the hell am I going to solve this equation without either one of those?
You can use 22.4 liters.
Equals how many moles?
1.
There you go. This tells me I can do that. Basically, it's sort of giving the game away. I can just assume I have 1 mole. I can assume any amount I want, but I might as well use 1 because 1's an easy number to calculate. Yeah, I'll just assume I have 1 mole. And so if I have 1 mole, so my N equals 1 mole, my V has to be 22.4 liters. And now I have everything I need. I've got temperature, I've got a pressure, I've got moles, and I got volume. I'm good to go. So here we go. So let's erase all of that. Figure out the density.
Ugh.
I have my molar. Hello.
什么？
Okay. So we have all the information we need to solve this. So now we can just figure out that the density is just going to be the molar mass times the pressure. We've set that at 1 atmosphere. That's standard. R, we know what R is. And T, that's standard temperature. So we have grams. Let me clear everything out. So when you set this up, you want to make sure, this is really important, and I keep mentioning this, but it's really important for these gas law questions. I'm going to have gas, I'm going to have grams, gas. I'm going to have grams on the top. And you see there's nothing in here to cancel that with. So I'm going to be left with grams in some way. So I have moles, I'm dividing by moles on the top. I'm also dividing by moles on the bottom. So because I'm dividing by moles on the top and bottom, they're in denominators on both the top and the bottom, I can subtract them. I can clear them out. Here, I've got atmospheres as a numerator. Here, I've got atmospheres as a numerator. That I can cancel. I've got where's my liters? Don't have any other liters there. So I'm going to be left with liters somehow. And then Kelvin, I've got Kelvin, both in the denominator, but one's a numerator and the other's a denominator, so I can cancel that. So basically what I'm left with is grams in the numerator, everything else is canceled out, and I have liters in the denominator. So grams per liter is going to be the end of it. So that is basically, that was the unit I was looking for. That's what density is measured in. So always make sure you have the units in. I know it's going to be a pain putting all these units in for R, but believe me, it'll save you a lot of trouble down the road. I'm constantly wondering atmosphere, liter, mole, kelvins, like how do they all go together? So I basically just had it tattooed on my arm. So now I can just look at it. So any questions about how to do these, how the units all sort of stack up together? Yeah, you're gonna have to be careful when you're doing these, especially things where mole in the denominator, in the numerator, and then mole in the denominator, in the denominator. So yeah, so be very careful with those. Everyone's understanding. Everyone's a genius.
So
I love it. Oh, yes.
the 0.0821, that is replacing R, correct?
That is R.
Yeah, that's, yeah.
Yeah. Mm-hmm. Yeah, that is the usual. That's the usual way R will be represented. Yeah, I mentioned if you just like Google like what is the gas constant R, you're going to get a whole bunch of different answers, and they're basically all dependent on what your measured pressure is. But since I think atmospheres is probably the most sensible way to do it, because generally your answer is going to be pretty close to 1, and 1's an easy number. This is the R we're gonna use. Oh dear, we're having doggy fun now. All right. So at 20 degrees, basically all we do. So we've got this answer at 0 degrees. So for 20, really all we have to do is change the temperature. We're dealing with it. So instead of 273, it's now 293. And so you can see that my density is now slightly different. Not a lot, but slightly. So you can see that these slight changes in temperature will have slight changes in gas units, whereas pressure generally will have accompany much bigger changes. So let me clear these out. So this was the method that people used to actually figure out what back in the old times, to figure out what the molar mass of gases were, because they didn't know, it's really hard to measure the mass of a gas, right? I mean, it's easy to measure the pressure, it's easy to measure the volume, but measuring the mass of a gas is really difficult, because generally you have to have a really huge amount of gas to have any sort of significant amount of mass. And so they figured out the molar masses by using this particular method. And so the molar mass was determined as the mass, and then just plugged in RT and PV. And that way they could figure out. Have fun, puppies. That way they could figure out how much a particular mole was. And at the end of the chapter, I'll show you another way, even easier way, to figure out what the molar mass of a gas is. So here's like a typical problem with this sort of thing, looking at a molar mass. So a lot of organic chemists will be dealing with gases. And so in this particular instance, we have an organic chemist, and she's got this colorless liquid. She doesn't really know what it is, but places the liquid in a flask and then vaporizes it in boiling water, and then fills up the flask with gas. So then she closes the flask, reweighs it, and gets this information. So that's the volume of the flask that she had. That's the temperature that she vaporized it at, and it was around atmospheric pressure. This is the mass of the flask before adding the liquid and vaporizing it, and this was or after, and this was the mass before. So just with this information, you can actually determine what that gas is just by measuring the mass of it. Because it's a gas, we know it obeys these particular laws. And so a very, very simple way of determining the identity of that gas would be determining its molar mass. If you know the precise number of its molar mass, then it's a fairly straightforward way of figuring out what it is. So how would we do that? So we put all our information together and then convert the units like we always do. So the mass of the gas was just the mass of the flask before and after. That's it. So this is how many grams we have of gas. She measured the volume of the container. So it's around a 250 ml flask, so it's a little less. And remember, we always convert to liters. Milliliters will always get converted to liters. And then since she used boiling water to vaporize it, the temperature was 100 degrees C. That's the boiling point of water. Now, measuring the pressure was around 1 atmosphere in the lab at the time. So you take all that information together and you just plug it in. So my molar mass is going to be equal to the mass, and here's my mass. R is always going to be the same, as long as I make my unit conversions properly. Atmospheres being the most critical. Atmospheres and Kelvin. You need to have Kelvin, always, always, always Kelvin. Plug everything in and we come up with 84.4 grams per mole. And if you do this accurately enough, you can get extremely accurate molecular mass. for the gas. And the more accurate you could measure it, the more accurate you can predict what exactly your product was. Any questions about how to do these things? Basically, just make sure you have the right units and you're halfway home. All right. So much understanding.
Wait, I have a question.
Sure.
So how do you know that that's the formula that you're gonna use? I mean,
Sorry?
how do you know that that's the formula that you're gonna use? Because if, for example, if you have the
Oh, sure. Yeah, great
formula-
question. Let's go back. Everything derives from PivNert. PivNert is our savior for this particular chapter. So as long as we remember PivNert, we don't really need to know anything else. So basically all we did to get to this was replace N. So basically what we're saying is that N equals PV over RT. Well, what's N? N is the number of moles. What's another way we can say number of moles? Well, it can also be the mass divided by the molar mass, or grams over moles. Right? That's the same thing. Number of moles is equal to grams divided by grams over moles. Would you say that's true?
Yes.
Right? So I want grams over moles. How do I do that? I basically divide or multiply each side by grams over moles. Basically do a conversion where my mass then moves over here and my grams over moles is now on this side by itself. Basically, I sort of multiply each side by the mass. That gives me moles, grams per mole, basically. Here, sort of. Let me do that one more time. Okay, so I have N is equal to PV divided by RT. Sorry, now I'm making mistakes. So N is equal to moles, which is also equal to grams divided by grams divided by moles. So this is the mass of my gas, and this is the molar mass of my gas. So these two things cancel. So if I multiply both sides of this equation by grams, then my mass in grams goes over here, and my mass in grams go over here, and what do I have left? Per mole. So now I have grams per mole equals my pressure, my volume, my mass, R, and T. Okay?
Got it.
Got it? Good, because I didn't have it at first. I was like, oh dear, she's got me. she's gonna make me do math. Math is hard. At least that's what Barbie used to say, until they made her stop saying that. Finally. All right, cool. Still got it. Excellent. Okay. So another thing we measure about gases that we haven't talked about yet is something called the mole fraction. And we sort of talked about mass fractions. Remember we were measuring solutions. One of the ways we measure solution is in percent, like mass percent, like the mass of our solute over the mass of the solution. Remember we did that? So like if we have like a 5% solution of sodium chloride, basically means we have 5 grams of sodium chloride in 100 mils of solution. Do the same thing with moles. So basically, when we want a mole fraction, we want the number of moles of solute in the total number of moles of solution. It's the same thing. So basically, what we would have to do is measure the amount of all the moles of every gas in the solution and how many moles of our solute gas would we have. Well, the nice thing is the pressure of each gas is exactly the same. Remember that they take up the same volume, they exert the same pressure. So really, all we need to figure out is how much pressure a particular gas is exerting. And that's called the partial. Yeah, beat them, would you? Oh, sorry, I'm not going to beat the dogs. So that's called the partial pressure. In other words, if I let all the CO2 if I had a flask of air, and I let all the CO2 out of it, but kept everything else in, the pressure would go down by however much CO2 I had in there. And by measuring the new pressure, I could then figure out how much CO2 I had by moles, because the moles of the gas are directly related to both the volume and the pressure. So the partial pressure of a gas is proportional to the mole fraction. So just like I said, if I can figure out some way to measure the pressure of just one gas in there, I can figure out what's the mole fraction of that gas in the solution of gases. And the usual way we do that is we basically do some sort of reaction that removes that one gas, or some other physical way of removing that one gas and then remeasuring the pressure. And then that tells us on a molar basis how much of that gas was there originally. So this is a way of basically measuring how much pressure water vapor gives us at different temperatures. Now this is going to be important, or would have been important if we were doing the lab in real life, and you would have determined R by doing a reaction that releases hydrogen gas. So how that would have worked is if you would have taken some magnesium ribbon and cut it off, polished it up, and reacted it with hydrochloric acid. And when you do that, it makes magnesium chloride, 2 moles of that, and the other product is hydrogen gas. So by figuring out the number of moles of magnesium, you can figure out how many moles of hydrogen gas you would make. Then we determine the pressure in the room, so we'd have P. We determine the temperature in the room, so we'd have T. And you would measure the volume of the gas produced by bubbling it through water into a test tube. And basically, we would measure the amount of gas, or measure the volume of the gas that displaced water and pushed it out. And so we would look at the gas. Now, what you would have had to figure out at that point is hydrogen is not the only gas in the tube. It's in a mixture. So because we filled it with water, it's not going to be any air in there. But we know that water has three different stages, right? It's a solid, it's a liquid, and it's a gas. And even at room temperature, a certain amount of that water is going to be vapor. And this tells us how much, this table basically tells us at every temperature, or most temperatures we're going to be measuring, how much of the pressure inside that tube would come from water. And so you would have realized, in an ideal world, where we weren't all stuck indoors, that you take the total pressure, so the pressure would be the room pressure, the pressure of the room would equal the pressure of the hydrogen gas you made plus the pressure of the water. Because no matter what temperature, even at 0 degrees, even when you're freezing water, some small part of it is exerting pressure. And so we can measure this pressure, and we call this the partial pressure of water at these different temperatures. So a partial pressure tells you of the total pressure you're measuring, that's how much of it will be water. And notice at 100 degrees, what's the partial pressure of water? Does that number look familiar? (760 torr), which is equal to 760 millimeters of mercury. That number sound familiar?
Yes. Because it's ATM.
One atmosphere. That's
Yeah.
1 atmosphere of pressure. Right, that's 1 atmosphere of pressure. That's how we define the boiling point. The boiling point of a liquid is when it all gets converted to vapor, right? I mean, that's what boiling is. You're converting the liquid to the vapor. Well, that means that the partial pressure of that liquid is atmospheric pressure. So it's the pressure of the water is atmospheric pressure, the water vapor. Now, in Denver, the atmospheric pressure isn't 760 millimeters of mercury, is it? It's less. Let's say the atmospheric pressure in Denver is around 650. You see why the boiling point of water is lower in Denver than it is here at sea level in San Francisco. That's why recipes for Denver and other cities like Boulder, wherever, if it's really high, like Mexico City, for instance, is very high altitude, they have to change all their recipes because things cook at a different temperature there. I mean, most of our cooking is based on, or at least, on the stovetop, is based on boiling water. Well, they have to cook things longer there because their water will boil at 95 degrees and our water boils at 100. And so if you want to cook something the same way, you have to cook it for a longer time, or you use a pressure cooker. And that's like in a pressure cooker, the pressure is much, much higher. And so you can heat the water to like 200, 300, 400, 500 degrees, and it stays a liquid because the pressure is super, super, super high. Any questions about that? Thought you might have been curious about, if you're going to cook an omelet in Denver, it's going to be different, You need to poach your eggs for an extra 30 seconds in Denver. It just ruins your whole life. So this comes back to the lab you would have done. Oh man. Am I way over time here? I am, aren't I? I completely lost track of the time. I'm terribly sorry. We'll end up here tomorrow. And so there'll just be a little bit left to do, and we'll start chapter 9. Yeah, I'm really sorry about running over. I wasn't paying attention. I was having too much fun talking about Denver. Any questions before we go? Everyone understands everything. Man, I must be like the best teacher ever. Just gonna pat myself on the head. Or everyone's completely tuned out. We'll pick this up again tomorrow. You'll have time for more questions tomorrow. Yeah, sorry about that. So yes, if you run into lab tonight, yeah, just stuff something in your head. Just go. And ask Dr. to grab all the embarrassing questions that I won't be able to answer. Okay? I will see everyone tomorrow night, and I'll see my lab class tomorrow afternoon. Okay?
Okay, see ya.
All right.
Thank you.